Hi again, this is Changster. Welcome to another episode of Math Learning on Simplifying Radicals. In this video, you will learn about how to simplify radicals of variable expressions. So let's get to it. Let's look at square root of x squared. Is it always true that the square root of x squared is equals to x? Let's recall the symbol, the square root symbol, and what it means. If you don't know what it means, you may have to refer to my video on evaluating radicals, and that explains to you what the square root symbol represents. So this symbol names the principal or positive square root of a positive number. So this is the principal square root or positive square root. So if you positive square root, considering square root of 7 squared, we know that that equals the square root of 49, and that gives you 7. And if the radicand is negative 7 squared, and that becomes negative 7 times negative 7 is also 49, and the answer is 7. In these two examples, you can see that no matter whether your x is a positive 7 or negative 7, the answer will always be a positive 7. This brings us to our next property. So if you take the principal square root of b squared, this answer will be the absolute value of b. So it's like there's a 2 here, and this 2 number, the index of the radical, and the exponent cancel out to give you the number or the variable b, and it has to be the absolute value of b or the positive value of b. Now let us consider taking the cube root of a variable. For example, when x is equals to 2, the cube root of 2 cubed would be cube root of 8, and that would give us 2. And when x is equals to negative 2, the cube root of negative 2 cubed is the cube root of negative 8, and that would be negative 2. When we take the cube root of a variable expression, we don't have to worry so much about whether or not the root will be positive or negative, because it will follow the original value of the variable. So you just have to put it as b. Let's look at how we can simplify radicals when the index is 4. So when x is equals to 2, the fourth root of 2 to the 4 is equals to 2. And when x is equals to negative 2, so here, if the fourth root of negative 2 to the 4th is equals to the fourth root of 16, and that equals to 2. Again, for this case, if we have the fourth root of b to the 4, we will need to put the absolute value of b, because we are taking the principal root and it has to be positive. This gives us the next property, which says that the nth root of b to the n is equals to the absolute value of b when n is even. When n is odd, the nth root of b to the n is just b. You will take the sign of the value of b. Let's apply what we've just learned by solving some examples. The example 1, the principal square root of 196 times y squared. We can apply the product of radicals to break it up into the principal root of 196 times the principal root of y squared. 196 is a rather big number, so you may want to find the prime factors of 196. 196 is an even number. If I divide it by 2, I'll get 98. And then I can continue to divide 98 by 2. I realize I get 47. So I can now just write the square root of 196 into square root of 4 times square root of 49. And if you take the principal square root of y squared, you get the absolute value of y. And when you break up the numbers, you get square root of 4 times square root of 49 times the absolute value of y, and that's 2 times 7 times the absolute value of y, and you will get 14 absolute value of y as your answer. In example 2, we are solving the principal square root of 36 times y to the 4th. So that can be broken up into square root of 36 times the square root of y to the 4th. And we know that the principal square root of 36 would give us 6. And x to the 4th can be expressed as x squared. So from here, you can write it as 6 times x squared. In this case, we don't have to put absolute value around x squared because x squared will be positive regardless of the sign of x. In example 3, we are evaluating the square root of 18 times a to the 3rd power. So we can break it down into the principal root of 18 times a to the cube, a cube, and we have to think about the factors of 18 that gives us a perfect square, and very nicely we can obtain 9 times 2. For a cube, we can break it down into a squared times a, and now square root of 9 times root 2 times square root of a times a. That would give us 3 root 2, and then we have absolute value of a times square root of a, and that would give us 3 absolute value of a times the principal root of 2a. Let's think about whether it is necessary to put your a as absolute value. In order for us to get the square root of 2a, this a has to be positive. Otherwise, we are getting into the world of complex and imaginary numbers, and we are not going to get into that. So in this case, we can just write our answer as 3a times square root of 2a, because we know that a has to be positive and the absolute value of a in this case here is unnecessary. In our 4th example, we are looking at the square root of 1.21 times k to the 6th. So I would like to express 1.21 as a fraction to help me here. So I can break it into 121 divided by 100 multiplied by k to the 6th. And from here, I can break it down into principal root of 121 divided by principal root of 100 times principal root of k to the 6th. And the principal root of 121 is 11, and principal root of 100 is 10. And think about what number square would give you k to the 6th, and that would have to be the square of k cubed. So here I can rewrite the fraction as a decimal. I'll get 1.1, and this k cubed. In this case, do I have to put the absolute value around k cubed? The answer is yes, because we want only the positive value of k. For number 5, the principal value of negative 9 times k to the 4th. In this case, think about, is there any number that when you square it will give you negative 9? And you can see that it is not possible, because 3 squared equals to 9, and negative 3 squared gives you 9 also. So in this case, I would say there is no real solution. All right. For our next practice, we'll look at more complicated examples. For number 6, we're looking at the negative square root of 48 times x to the 8th times y. So from here, I can write it as negative square root of 48 times square root of x to the 8th and square root of y to the 7th. So from here, let's look at the factors of 48, whether you can locate a perfect square. So 48, I know that is divisible by 4, so I'm going to get 12 here, and 12 is divisible by 4. I end up with 3. So very nicely, I know that 48 can be broken into 16 times 3, and for x to the 8th, we can write it as the square. That would be x to the 4th square. And for y to the 7th, I can break it up into y to the 6th times y1. The reason why I want y to the 6th because we can express y to the 6th as a square of another expression. So from here, the second part, we know that 16 is 4 square, and we have square root of 3 and the square root of, so there's a 2 here that we don't see, a square root of x to the 4th square would give me x to the 4th, and now I can break it, the last expression in y to y to the 6th times square root of y. And again, there is like a 2 here that we don't have to put, and square root of 4 to the square would give me 4, so this is negative 4 here, and the root of 3, and we have x to the 4th. There's no need for us to put this as in the absolute value sign because x to the 4th is always positive. And for here, let's the y expression, think about the square of which expression would give me a 6. So it has to be y cubed squared because you're applying the power of a power property here, and you get square root of y. And you continue to simplify the expression, so you get negative 4 square root of 3 x to the 4th, and again there's like a 2 here that you don't see, and then the expression in y becomes y cubed and square root of y. So we'll put the like terms together. You could see that negative 4 and x to the 4th and y cubed, they are numbers, so you can put them together. And there's a principal square root of 3 and square root of y, and there's a name for terms in root of 3. These are what we call surds. Surds are square roots that are not rational, so they are irrational. So you can get a whole number or a fraction from taking the root of those numbers. So basically they are the square root of non-perfect squares. Or for cube root, we're looking at cube root of numbers that are not cube numbers, such as 2, or say cube root of 10, but of course cube root of 8 is not a surd because its value is equal to 2, which is a rational number, and 2 can be expressed as a fraction. Continuing with the example in 6, we can now write it as negative 4x to the 4th y cubed and the square root of 3y, and that will be the most simplified expression for this example. For number 7, let's break it down into the cube root of 1000 times the cube root of a to the 4th and the cube root of b to the 5th. So we know that 1000 can be written as 10 to the 3rd. So, and a to the fourth can be written into a cubed times a, and b to the fifth can be written as b cubed times b squared. Index of the radical is equals to the exponent of 10, so we can simplify it into 10 is equals to 10. And again, for a cube, we can, because the index is a cube and this is a cube, and we can write it as a. And for b cube here, and the cube root of that will give me b, and the cube root of b squared stays as the cube root of b squared. So this is my final answer, and the most simplified expression for example 7. For number 8, we are looking at 2 times the cube root of negative 48 times b to the 7th. So 2 stays as a product. Let's look at what are the possible factors of 48 that can be a cube number. So I'm going to try writing 48 is divisible by 2, and I get 24, and I can divide it by 2 again, I get 12, and I can divide it by 2 again, and I get 6. Negative 48 can be written as negative 2 cubed times 6 times the cube root of v to the 6 times v. So if I simplify this, I'll end up with 2 times the cube root of negative 2 cubed times the cube root of 6 times the cube root of v squared to the third, because that's v6, v to the 6, and then we have the cube root of v. So from here, I end up with 2 times negative 2 times cube root of 6 times v squared times the cube root of v. And the answer in this case will be negative 4 v squared times the cube root of 6v. Before we look at our last example, some of you may feel that this is really complicated, and is there an easier way to solve this? I have a shortcut for you to use, but I would really prefer you to really understand it. But if you really feel like the shortcut will help you, then you may use it. The shortcut uses this property of indices. When you have the nth root of b to the m, you can write it as b, the exponent of m divided by n. If you want to understand how this property comes about, you may refer to my video on indices, on fractional indices, to understand how we can convert from the radical form to the index form. So from here, we will look at example 6, how we can simplify the square root of the variable expression. So here you can see that 8 is the exponent, and there's like a 2 here that we don't write for the index of the radical. So when you do 8 divided by 2, you end up with 4, and 4 is the exponent of the x here. And for y to the 7th, when you do a square root of y to the 7th, so you're actually, there is a 2 here that we are not writing. So again, you can look at it as 7 over 2. That gives you, if you divide 7 by 2, you get 3, and then remainder 1. So the 3 is the exponent of the y that is outside the radical, and the 1 is the exponent of the y in the radicand. Let's see how this works for example 7. So this is a to the fourth, we're taking the cube root, so you take 4 divided by 3, 3 goes into 4 one time, and you have a remainder of 1. So you can see the 1 here is the exponent of a outside the radical. And there is an a to the first power outside the radical. And I realized that I did not have my a here. I forgot to transfer my a down here. So I made a mistake in my work. So good. This one way you can check your answer. So it's 10a(b) to the cube root of ab squared. Okay? And for b is, I'm going to use a different color now. So let's say I'm using blue. b is to the fifth, so I take 5 divided by 3, and 3 goes into 5 one time. So the remainder is 2. So we can see from here, 1 should be the exponent of b outside the radical, and 2 is the exponent of the variable inside the radical. So for number 8, we take 7 divided by 3, and we know that it is 2 remainder 1, so 2 should be the exponent of v outside the radical, and 1 is the exponent of v under the radical. So this is how this works. For our last example, we are looking at the fourth root of 80 times m to the fourth times p to the seventh times q to the eighth. So let's apply the product of radical property to break down or simplify each radicand. And here we're gonna have, so we have the fourth root of 80 times m to the fourth times the fourth root of p to the seventh times fourth root of q to the eighth. And let's think about what are the possible factors of 80 that can give you a perfect square. So, sorry, not actually a perfect square, the fourth square. So 80 we know is divisible by 2, and I'll get 40. And 40 is divisible by 2, I get 20. And 20 is divisible by 2, I get 10. And is divisible by 2 to give me 5. So 80 can be written as 2 to the fourth times 5. And the fourth root of m to the fourth would be m. And in this case, I would have to put the absolute value sign because we are looking at only the positive value of m. And for the fourth root of p to the seventh, I can break down into the fourth root of p to the fourth times p to the third. And for q to the eighth, let's break it down into q squared to the fourth. And the expression can be simplified into the fourth root of 2 to the fourth times the fourth root of 5 times the absolute value of m times the fourth root of p to the fourth times the fourth root of p cubed times, in this case, for the fourth root of q squared to the fourth, I can just write it as q squared. Here we will not have to put the absolute value sign around q squared because the square of any number, whether they are positive or negative, is positive. The fourth root of 2 to the fourth is equals to 2, and fourth root of 5 remains as that, and then you have absolute value of m times, again this is the fourth root of p to the fourth, and in this it will be equals to p and the fourth root of p cubed. We don't have to put the absolute value sign around the p in this case because in order for p cubed to exist as a real solution, it has to be a positive value. And for q squared, it will remain as q squared. And now we will put the radical terms together and non-radical terms together. So in this case, it would be 2 times the absolute value of m times p times q squared times the fourth root of 5 pq. And if you would like to use the shortcut method, you can think about the exponents of the variable in the radicand. So for example, here we have m to the 4th, p to the 7th, and q to the 8th. So for m, and you will take 4 divided by the index of the radical, and you end up with 1, and that is the exponent of m here. And for p, you write it as 7 divided by 4. In this case, you get 1 remainder 3. So 1 is the exponent of the p outside the radical symbol, and the 3 is the exponent of p under the radical symbol. And for q to the 8, we write it as 8 divided by 4, you get a 2. So this number 2 is the exponent of q outside the radical symbol, and there is no variable q in the radicand. We have reached the end of my video on simplifying radicals. Do subscribe to my channel, and let's learn math together.